Good, now it's working. So this story of mapping the cosmic evolution with gravitational waves, you have heard two topics, both of them going from low redshift to high redshift universe, touching upon how we can do some kind of aspects on measurement of Hubble constant or so-called Hubble parameter, and also about the overall evolution of the universe. But the problem is, it's a very difficult problem to track. We have dark matter halos from which I need to form galaxies. From galaxies, I need to form stars. From stars, I need to form binary black holes. Extremely astrophysical complicated system will be ended up in an extremely simple two objects binary black holes, which can be characterized by mass, spin. So far, enough to explain the observations. And of course have distance from them. So it really comes to mind that, well, I have a bunch of stellar graveyards, and how am I going to use that to study the cosmos with a across time and across mass scale? Okay, so we'll use this particular diagram to explain, to go through the talk. And if I put some detectors over here, these are the bands which you see by LIGO. These are the bands we see by PTA as we speak. There are observations being made. And in future, these are other bands will open up. So what can we really do in the area of cosmology? I will divide the problem into two. Cosmology of black holes and cosmology with black holes. So let's start with cosmology with black holes. What's the game here? I would like to use black holes as a probe. You can change the word black hole to any gravitational sources. It's not important. Let's stick to black holes for today's talk. I would like to use these to trace the evolution of the universe, and to an extent, coming up to the final point of most of the cosmological results so far being presented, is to get to the energy budget of the universe. How do you do that? A couple of techniques being already talked by Archishman and Tit in the last two talks. What we will be talking about is a technique which explores the spatial clustering between gravitational wave sources and galaxies. It's a friendship between two experts. Gravitational waves are great in measuring distances. Galaxies are not. Galaxies are excellent tracers for measuring redshifts from a spectra. Black holes are not. But both of them talk to each other because they form at the places of the universe where they're highly dense. So I will have an intrinsically correlation between these events. As a result, thanks to LVK, in one side getting us order tens, hundreds of binaries now, and other side we have sky surveys such as DAISY, we have already data, SphereX is going to have data very soon, Euclid going on, LSST going on. We have a large function of galaxy surveys coming up, good redshifts, good luminosity distance, and we can start talking about spatial clustering between them by using cross-correlation technique. This talk is not about giving you details. The next 30 minutes is there to ask me any questions on this. What it really tells you that I can use the spatial clustering between gravitational wave sources and galaxies and obtain the true redshift and the inferred redshift pretty well in the coming and future detectors with LSST and LVK combination, LSST and DAISY combination, LVK and DAISY combination, and also for future detectors. What do? You go to higher redshift from in future detectors. At lower redshift with the current detectors, galaxy surveys are ahead of us. We can get to a pretty good clustering redshift measurement. This is the work done by Afroz. He's right over here. He spoke yesterday during his Sparkle poster session, where he has shown that how well we can get this measurement and how well it will lead to the measurement of Hubble constant from LIGO, Virgo, Kagra, and from CET. It will be a measurement of a few percent. This is Hubble constant plus some other parameters. These are those parameters which are marginalized, which takes into account omega matter, dark energy equation of state, or modified gravity. So if you don't allow many parameters to vary, your errors will go down. Bottom line is that we now have a technique which will work if we have well localized binary black hole systems. LIGO Virgo Kagra and of course LIGO India is going to be instrumental in making these measurements. Only 2 detectors or even just 3 detectors is not sufficient to get these numbers with the precision we're being done here. What do we stand today? We have about 90 events in GWTC3. About 8 of them are very well localized. By very well, I mean less than 30 square degrees. If you use those, you can get a first constraint on the Hubble constant from the cross correlation technique. And our current measurements is shown in black. Not very comparative, of course, but this will change as per the forecast we expect in the future. Moving on, unveiling dark energy. This was yesterday came up. Today also morning it came up. Even if we get the very good inference of dark energy equation of state from non-gravitational wave surveys, we will always face a major challenge that are we able to take care of the calibrations properly. All surfaces or all tracers are impacted by astrophysical properties, primarily maybe metallicity, as has been shown by many people. Fortunately, we are not in that era. Gravitational wave sources in future will be able to map the entire expansion history of the universe up to high redshift. This is the h of z over 1 plus z. This is the rate. It's like a dot. This tells me with future detectors I can go up to high redshift. This is done for the next generation gravitational detectors, where we will be able to measure dark energy equation of state as a reconstruction, not only as W naught and WA. As Steve mentioned in his talk as well, it's an excellent phenomenological model to calibrate, to measure the low redshift part, and not a great thing to do when you have the access to the high redshift. Discovery of dark energy equation of state will not rely on just 2 parameters, W naught and WA. How does it compare? This is the comparison of all state-of-the-art EM surveys. This is what we can get from gravitational wave, from bright sirens, and from dark sirens, again from approach. You can see the smallest error bar in a calibration-free way will be accessible from gravitational wave observations only. And for cross-correlation techniques, it is limited by the galaxy surveys available. As a result, the error bar are comparable. Okay? But bright sirens are possibly the best way, in my opinion, to go for dark energy equation of state from third generation. Moving on, I have a little bit or several minutes left. The second part of my talk, cosmology of black holes. Tracing the cosmic evolution of black holes. We possibly should not forget this. See, cosmology is not only about measuring background parameters. High redshift universe is a completely unknown thing for us. From very beginning, we have started not understanding how quasars at the highest redshifts has formed. And possibly, we can go somewhere there. So now I will talk about these 2 bands, how they are useful to understand the cosmic evolution of black holes. So how do we go with this? So let's at first start with stellar mass binary black holes and how are they related to the host galaxies. So this mapping I have done from dark matter, galaxy, star formation rate and black holes. How do I connect it? What is underlying physics? I play with a large number of astrophysical knobs to get a few observable quantity. That observable quantity can be characterized in terms of gravitational wave bias parameter. This is the work done by Amir. This simulation, this is a file which is showing you if you change the host property of the gravitational wave sources with galaxies. This is the stellar mass proxy, and these are the slopes at which at the high end they get populated, higher end of the galaxies. At the lower end, how they get populated, then how the black hole bias parameter will change. It's a very complicated part to see, but what you're trying to see that there is a trend of low bias to high bias at low redshift. This is done from observation of Y supercos. This is a data-driven approach where you take the galaxy catalog, put your best astrophysics known, and try to ask what will be the prediction for bias parameter that I can measure. That's the plot which you are seeing. This has gone in his PhD thesis, which has shown how well I can measure the galaxy bias as a function of redshift evolution, and galaxy bias, well, with respect to galaxy bias, how the gravitational bias will look for different astrophysical scenarios. In short, if galaxies are very bright, are dominating the population of binaries, in comparison to if they are mostly at the center end as well, my bias parameter will become more close to 1 as I start seeing or start populating black holes with all kinds of galaxies. If I only populate the high end, the bias will be higher. There is also a catch for primordial black holes, ask me later. And this is something that we can measure with the help of gravitational detectors in synergy with DAISY Sphere X particularly. This is a work with Cigar and Christina back a couple of years, where we have shown that as we start measuring Hubble constant from the cross correlation technique, measurement of galaxy bias will be a natural proxy. We will naturally go through a scenario and start inferring it for the very first time. We do not know what this quantity is. We marginalize and we do it together, but we expect to see a redshift evolution, which is captured by the parameter alpha, and the BGW is the normalization at redshift 0. Moving on, I have a couple of minutes left. Let's talk about the PTA range, what absolutely evolution it can bring in the understanding of black hole formation. Thanks to Teet for setting up the stage. Yes, high redshift universe is extremely important. Particularly, gravitational science can bring answers to some of the open questions. Cosmic, so we will start from the high end because that's the thing we detect now. 20 years down the lane, if we detect stellar mass black holes, we have a place to develop new techniques. So I start my work with, let's say, supermassive binary black holes now. Key questions, everyone in this room who has done Cosmology 101 has possibly studied how black holes in the early universe have formed, how they have evolved. We don't know. How early, how heavy, and how many. So the problem is, if I give you a galaxy distribution, yeah, there is many galaxies there. Some of them will have a black hole binary going on. They will emit gravitational wave signal, and this signal at the smallest scale is driving the observed signal in the gravitational wave map, which is a large angular scale map. That means physics at very small scale is getting driven by the very small scale physics is driving the large scale signature. So that's the difficulty we have. We observe the signal in gigaparsec scale, which is driven by milliparsec scale physics of two binaries coalescing. And on this particular effort, there is a bunch of works being done by my PhD student Mohit in collaboration with several people, including people from ICTS. I hope Akash is here. I don't see him. So what is the idea? Idea is you bridge across scale. You start from the largest scale gigaparsec simulation and you stitch it with medium scale Romulus simulation, hydro simulation, which takes into account dynamical friction. There you capture these black holes, you generate the gravitational wave signal, generate the gravitational wave Fourier domain spectrum, and generate the gravitational wave map. So a small scale physics gets captured in the large scale universe to predict what kind of signal I would expect. What kind of signal should I expect? I will start expecting gravitational wave stochastic background amplitude, which has a tilt because of how much energy has been lost by interacting with the environment and how long that procedure is important. These two drives the amplitude, and this is what it sets the typical value would expect from the upcoming survey as PTA goes to scale. Moving on, spatial and spectral anisotropy. At every frequency of PTA, I can construct my sky map if I do a narrowband search, and I will start seeing structures in the gravitational wave angular power spectrum, which will be short noise dominated in some regime and will be highly non-Gaussian. Anisotropy sky map dominated by a very few sources at the high frequency will be extremely non-Gaussian. As a result, now the issue comes is that if I would like to explore this quantity of cosmic evolution of black holes in the universe, How do I do that? I would need to answer 3 questions particularly: how many, how heavy, and how early. The how many and how heavy part starts getting answered partly from the stochastic gravitational background amplitude, and how early the black holes are forming. Thanks to the galaxy surveys, which starts bringing that to us. Galaxy surveys up to high redshifts such as LSS and in future from SKA, they are the tracer of the underlying matter distribution. So one can use cross correlation between gravitational sources and galaxies, which will directly probe how early supermassive black holes can form in the universe. And this is the plot you are seeing for SKA prospects, answering how many and how early they can form. This is, right now the error bars are infinity, there's no measurement. We'll be in a scenario to put constraint on the redshift evolution of the occupancy fraction of black holes at high redshift, and also the mass distribution of supermassive black holes as a function of redshift, telling how heavy and how early. With this, I will end my talk saying that it's a great time to explore the universe using stellar graveyard, both by events and by stochastic signal. We have heard about the different bands, but there are also interesting bands available in cosmic microwave background, and it's really a multi-band search which we are now doing. And with this, I'll end my talk saying that stay tuned for discoveries with new messengers. Thank you.
Thank you, Suvodip. Yeah. Time for a question.
Could you put up your slide where you showed the effective sort of environmental effects on the PTA background? Maybe say a little bit about that slide. And as you know, Nanograv announced compelling evidence. So which of these models would be compatible with that and which would not be?
Very good point. So the problem is, this is only astrophysics. And there is a hat of cosmology, which will tell you I can have some cosmological background with some peak, some shape. So if you ask the question of, if I give you just astrophysics and switch off cosmology completely, that would be a scenario which is somewhere here. So we have around 4 nanohertz, a little bump. That is difficult to explain, unless it's an individual point source. But else, a signal of this kind is something which will agree with the data, and not this. This is seen by all the PTA measurements. You will see it says universal slope has been ruled out. It must be ruled out. It's not a discovery. It's an obvious statement that no supermassive black holes can ever form without any baryonic matter in presence of them. Presence of baryonic matter will tilt, and we have seen a tilted spectrum. What's next to be done is to really understand the competition between cosmological background. I hope some of the later speakers will talk about this, and astrophysical background. So where is that shape and where is that amplitude needs to be figured out. But to answer your question is yes. So these results are obtained post, right? So we have made sure that it agrees.
Hi, Suvodip. I'm here. Okay.
Hi.
So yeah, can you go back to the measuring cosmological parameters in a calibration-free way?
Dark energy.
Yes.
Sure.
So, and you're, I guess, pinning your bet on binary neutron stars, but bright Saturns, right?
Yes.
So why specifically are you, like, for example, what exactly are you assuming for this population distribution to be?
Good.
Like how high in redshift, how many of them you're involving, etc.
Excellent. So we start with, question is, what population of the bright Sirens do we expect? We expect a delayed distribution from Maddow-Dickinson star formation rate for both neutron star and black hole systems with their corresponding binaries, or the binary neutron star or neutron star black hole or binary black hole. We go up to high redshift that is currently limited by Vera Rubin Observatory. Of course, can make even more final statement than that, because we are now limited by galaxy EM surveys. Future generation detectors will go deeper than any surveys proposed. What's important to realize is that dark energy equation of state, where the measurement is coming from. The measurement is not coming from here. You see the redshift error is large because the distance error goes up, as you expect. Stuff is coming right over here. Why is it interesting? That's the place where whether W naught is positive or negative drives your slope. As a result, because I have, say, thousands of tracers which measures luminosity distance without any extra calibration, like in metallicity, I can discuss about this in details. What's the key take home is that I can get to this slope without any calibration up to a redshift 1:. Interesting for dark imaging. As a result, I have not shown the results here. It is there in Afro's paper, which shows you that with gravitational wave astronomy, we will not be only measuring W0 and WA, but we can start expanding it to higher orders and actually completely reconstruct it. There is a usual problem. You possibly have heard many people talking about this using pause. Even the recent paper by Paul Steinhardt saying that don't use W0 and WA. Why? It's not a good parameter. It misses the physics at the important place it's required to be fitting well at high redshift or below above 0.5 to 1. We will be able to solve that problem. It's the entire this community which will solve the problem in long run when third generation detectors will be available.
Thank you.
Thanks.
Okay, thank you, Suvodip. This was a very nice talk.